Introduction in Chemistry 20 Review Charged Lewis dot Structures for the BR18 assignment. When working with charged molecules or molecules with no overall charge, but individual elements are charged, the earlier method of drawing Lewis structures will not work. These structures must be drawn utilizing the following rules. Draw all the elements with their correct number of dots, just like we have already been doing. If there is a negative charge, you must add dots to meet the magnitude of the negative charge, meaning a -2 charge has to have 2 dots added to the structure. Dots are normally added to elements that are furthest to the right of the periodic table, as they typically want to gain more electrons. If there is a positive charge, you must take dots away from elements to match the charge. And again, typically, the elements that are on the left side of the periodic table want to lose electrons, so they typically will take the positive charges if possible, but it's not always the case. Then you'll lasso single dots together following the same method that we used in BR16 and 17, and then we write the formal charge on each individual atom, putting negatives by the elements that gained electrons and positives to the atoms that lost electrons. And if the molecule has an overall charge, remember we place square brackets around the structure and we write the overall charge outside the brackets in the upper right-hand corner. Example 1, oxalate, C2O4 with a 2- charge. The carbons have 4 dots, so they can make 4 bonds. The oxygen has 6 dots, so we know it's able to make 2 bonds. So since carbon can make more bonds, we'll place it on our paper first. So I'll draw my carbon and my second carbon, and I'm going to write the oxygens, the 4 oxygens that I have spaced out around the carbon. So maybe one on the top, bottom, looking pretty good. Now I have to add in some dots. I have 2 dots to add. Now oxygen is further to the right-hand side of the periodic table. It's closer to the noble gas. All it has to do is gain some electrons. So I'm going to predict that the oxygen is probably going to be picking up the electrons. So again, I will space those out around the molecule. So I'll give one down bottom right-hand corner, and then if I put it on the bottom right-hand corner, I'll put my other spare dot maybe on the upper left-hand corner. Now I can start lassoing and see if what I've done will work out. So I'll join the 2 carbons, and maybe I'll join the carbon to the top oxygen, and I'll do the same thing on the opposite side. I'll bond the carbon to that oxygen that can only make 1 bond now because it picked up that extra electron. And now I wind up with, on the upper right-hand corner, a carbon that can still make 2 bonds and an oxygen that can still make 2 bonds. So I think I'm going to put a double bond in there. And bottom right-hand corner, I also have a carbon that can make 2 bonds and an oxygen that can make 2 bonds. So I'm going to make a double bond there. Yeah, it looks like all the singles have found partners. So now I have to draw this thing out. If I look at either carbon, they're making a single bond, double bond. So that means I'm going to have 120 degrees between everything organized around the carbon, because there's 3 things around each carbon, which is again, single bond, double bond. So I'll start by drawing my 2 carbons being connected by a single bond. Then maybe I'll add the single bond in going up to the oxygen. And notice that I made sure that the dots, when I look at the oxygen, are spread out 90 degrees from one another and 90 degrees from the bond. And that carbon is also making, aside from a single bond to an oxygen, it's making a double bond to an oxygen. And again, that oxygen at the bottom has 3 things around it: double bond, lone pair, lone pair. So I make sure there's 120 degrees between each of those. The carbon on the right-hand side is making a single bond to the oxygen in the bottom corner, and it's making a double bond to the oxygen in the upper right-hand corner. Now, I have to identify inside my picture who picked up the extra electrons. So that is the oxygen in the top left and the oxygen in the bottom right-hand corner. Now I'm going to put big square brackets around this entire thing, and I'll write 2- outside the brackets. Now, I'm almost done. The last thing I got to do is list the geometry. And each carbon is taking a trigonal planar geometry. So instead of writing it twice, since trigonal planar is the only geometry inside of this molecule, I can just write trigonal planar. Example 2, CH6N with a positive charge. Carbon, 4 dots, makes 4 bonds. Hydrogen, 1 dot, makes 1 bond, and nitrogen, with its 5 dots, is able to make 3 bonds. So I'll put carbon down on paper first, and then nitrogen, and I'll start adding in my hydrogens last because they make the fewest bonds. So 1, 2, 3, 4, 5, and I don't know where I'd put that 6th hydrogen. But we do have a positive charge, which means I'm supposed to take an electron out of the picture somewhere. And if I take it off that N, then I can add the 6th hydrogen on the bottom. That way the carbon and nitrogen bond, the carbon at the top bonds to 3 different hydrogens, and the nitrogen at the bottom is able to bond to the 3 hydrogens down there. Now the carbon is making 4 single bonds, which means I have to spread things out 90 degrees on my paper. And the nitrogen is also making 4 single bonds, which means there has to be 90 degrees between each one of those bonds. So I'll write carbon with 3 hydrogens and a nitrogen spread out 90 degrees, and then I'll add 3 hydrogens to that nitrogen, so they're all spread out 90 degrees. I need to put a positive charge by whoever lost the electron, and that was, nitrogen. So I'll put a positive by nitrogen. It's a nice big square brackets and a positive charge outside of the brackets. Now, the carbon is making the tetrahedral shape. Nitrogen is making the tetrahedral shape. It's the only shape inside this molecule, so I just have to write tetrahedral. And this question is now complete. Sulfur dioxide. Sulfur has 6 dots, so it's able to make 2 bonds. Oxygen also has 6 dots, so it is also able to make 2 bonds. So which one to put on my piece of paper first? Well, if it's a tie, we're supposed to put the least abundant element in the middle. So there's only one sulfur, so we'll put sulfur down. And the oxygens, I have 2 to place, so I will put 1 at each of the bonding sites that sulfur has. So I'll put 1 on the right-hand side and 1 at the bottom. And now the sulfur can bond to the oxygen on the right, and the sulfur can bond to the oxygen at the bottom. And look at that. The O's that are left are each able to make 1 bond. So ding, dang, dong. There we go. So sulfur is connected to the oxygens with single bonds, and the oxygens are connected to each other. And it was that easy if we were allowed to have a circle that small, which we aren't allowed because we said the smallest circle that we can make would have to contain 5 elements holding hands. This circle is way too small, so that is not going to work. We're going to have to go back to the drawing board. So what can we do? Well, we know this is charged molecules, and we don't have any charges here. So how do we get a charge? Well, we get a positive charge if someone loses an electron. We get a negative charge if someone gains an electron. And since SO2 is in the charged section, I'm going to have to assume that must be what happened. So what can I do here? Well, the element in the middle usually makes the most bonds, or does make the most bonds. It has to. If it's in the middle, it makes more bonds than the ones that are on the edge. So if sulfur's in the middle, we need it to make more bonds. And how do I get it to make more bonds? Well, if I take an electron away from it, it can then make 3 bonds instead of 2. So I'm going to try that. I'm going to take an electron off of the sulfur, and I'm going to move it to the oxygen. Now check out this PowerPoint magic. Oh, that is impressive stuff. That is impressive. All right, so that oxygen on the bottom now can only make 1 bond. So I'm going to lasso that with the sulfur. And that sulfur in the middle can make 2 bonds, and so can the oxygen that's left. So we're going to have a double bond going to that oxygen. So sulfur is in the middle with a lone pair, single bond, double bond. So that's going to have to go in that Mercedes shape, 120 degrees in the angles. So I'll draw sulfur, 120 degrees between the lone pair, single bond, and double bond. The double bond has that oxygen with two lone pairs, so I make sure that they are also spread out 120 degrees. And the oxygen at the bottom has three lone pairs and a single bond, so 90 degrees between all the stuff that's connected to that oxygen. I have to remember to write my charges in. Sulfur lost an electron, so that means it must now be positive, and oxygen gained the electron, so it must now be negative. No square brackets are required because there is no overall charge. But I do have to give the name of the shape, and sulfur is our central atom, and it is taking the bent shape. Example 4, phosphate. P has 5 dots, so it can make 3 bonds. Oxygen has 6 dots, so it's able to make 2 bonds. So I know P is going to go in the middle. It makes the most bonds. I'm going to place an oxygen at each one of those bonding sites. Now the last oxygen, I'm not exactly sure where to put that, but I know the oxygen at the bottom has an open bonding site, so I'll place this oxygen by that open bonding site. Now having a -3 charge means I have 3 electrons I can add to my picture. So I'm going to place them on the oxygens that are furthest out because stuff that's further away typically makes less bonds or fewer bonds. So there's a dot there, dot here, and a dot there. Now, the OP can come together here, and the phosphorus can bond to the oxygen on the right and the one on the bottom. And that O at the bottom can bond to the other O at the bottom. And now everybody is connected, and everybody has single electrons that are being shared or lone pairs. So everybody's happy. So that means my phosphorus has 4 things around it, a lone pair and 3 single bonds. So I'll draw that phosphorus with 90 degrees between everything that is connected to that phosphorus. I'll put in the oxygen on the left-hand side, a lone pair, lone pair, lone pair, single bond, so that's 90 degrees between each thing. Oxygen on the right-hand side, same situation, single bond, lone pair, lone pair, lone pair, that's 4 things, so 90 degrees between each. The oxygen at the bottom that the P is connected to has a single bond, lone pair, lone pair. So again, that's 90 degrees between each one. And the oxygen bottom right has lone pair, lone pair, lone pair, single bond, which is 4 things, 90 degrees between each. Now I'm going to put a negative by each one of those oxygens that picked up an extra electron. I draw big square brackets, and I put the charge to the outside. Now I have to identify the shapes. Phosphorus has 3 single bonds and a lone pair, and that makes it trigonal pyramidal. The oxygen at the bottom, in the middle, at the bottom, it has 2 single bonds and 2 lone pairs. That gives it a bent shape. And then we're good. Example 4 again. Now let's take a look at how this might be done by someone else. So we got a P here, and we're going to add those O's in. But remember, I added the last O to the bottom right-hand corner. But someone might be inclined to stick it on that top P. And then they'll start adding in their dots. And then they'll say, how am I going to get that P to bond to the O at the top? And thinking back to the previous example, we were able to move electrons around. So if I take an electron off the phosphorus and move it up to the oxygen, then I can lasso those guys and these guys and those guys and those guys, and ba-ding dang dong, done. So I got a phosphorus that is making a single bond to 4 different oxygens. And these guys have all picked up extra electrons, and the phosphorus lost an electron, so it now has a positive charge. So I put some square brackets around it and write a 3- up in the top right-hand corner, and the name of the shape is tetrahedral. And this is Well, rational, it makes sense, but it would be considered wrong. Because, oh, wait for it on the next slide. So both of these have plausible bonding structures. But why would the one on the left be favored over the one on the right? Why would the one on the left be considered correct when the one on the right is considered incorrect? And the reason is whichever one gives us the fewer internal charges will be considered the correct structure. So since we have 3 negative charges on the left, but on the right we have 4 negatives and a positive charge, the structure on the left has fewer internal charges. It is preferred. That would be then the correct answer for this question. And that's the end of the lesson. You're going on to draw all those charge structures in BR18.